let's start the class of today. So first I want to remind everyone about the last theorem we were trying to show. So what we are, reminder, we were trying to show the following. So consider a subset of some lambda 1 that is a subset of lambda 2, and this is a finite subset of ZD. And then we have the following chain of inequalities for the expectation value of the plus boundary condition local Gibbs measure on lambda 2 beta h. Okay, this is less than lambda a, so sigma a lambda 1 beta h plus. So what this shows is that when you increase the size of your finite set, then the expectation value will also, when you increase the size, the expectation value actually decreases. Okay, so what were the main steps of the proof? So we wrote the Hamiltonian with plus boundary. We define it first. We defined a field H prime, and this field was defined as H prime x, and was given by, for x inside lambda 2, and was given by H prime x was some number t, some positive number t, real number, so positive, if x was inside lambda 2 minus lambda 1, and it was 0 otherwise. And we showed that when you increase the field, since this is a positive field, when you increase the field, what you actually get is something larger than what you had before. Okay, and then we wrote the Hamiltonian function with plus boundary condition. Okay, as using the following expression. So we had the sum of two terms. So this is the first Hamiltonian on the local box with a different boundary condition. Okay. So okay, first, to not confuse everyone. So what we did is we split the configuration space in the larger box into two. So the configuration space and in the smaller box, and the configuration space in the remaining box. And then doing this, we can write the sum over all the configurations here as being a sum over all the configurations, say eta, summing over the remaining set, and a sum over all the configurations, let's say tau, over lambda 1, okay? And in this way, using this notation, then we wrote the Hamiltonian function, with plus boundary condition on the larger box, depending on beta and h plus h prime. So the Hamiltonian function, in this place, it was the sum over the it is equal to the sum of the Hamiltonian on the smaller box. Now only we fill h, but now we pay the price. The boundary condition now is eta, but it's eta only between lambda 2 and lambda 1. Outside lambda 2 is still plus boundary condition. And we add some term here that I wrote something like this, beta t, that only depends on this guy over here. And this remaining term, so this is a sum, this depends on tau, this depends on omega, plus we can write like this. So, and this term right here, beta t, the remaining term, it was the sum minus the sum of jxy, xy inside lambda 2 minus lambda 1, eta x, eta y, minus the sum jxy, x inside lambda 2, lambda 1 times y outside lambda 2, eta x, and then the field, the non-constant field, the remaining part of the field is written as h plus t, okay? H plus t times eta x, x inside lambda 2 minus lambda 1, okay? So, yeah, this is right. So notice that when we write, so we use this decomposition to write the expectation value of sigma a lambda 2 beta h plus h prime as a sum over all the configurations here, and then we have the exponential of the remaining term, lambda 2, lambda 1, beta t, eta, times the partition function on the smaller set, beta h, with boundary condition omega, no, eta, divided by partition function, the partition function in the larger C, h plus h prime plus, and now times this. Lambda 2, no, lambda 1, beta h plus. We wrote like this. So now we stopped it more or less at this point where we were analyzing what happens to this term over here. So let us look to this partition function. So the partition function, lambda 2 beta h plus h prime This is the sum over all the configurations here. Sorry, lambda 2 exponential of minus h with the plus boundary theta h plus h prime calculated at sigma. Okay? But now we can use a similar decomposition, right? So this can be written as something like the sum overall theta, let's say, okay. I will use sigma prime inside lambda 1 exponential of we have a minus. So we have the exponential of minus the remainder beta t. Now depending on the boundary condition theta times what? Times the exponential of minus h lambda 1 beta h with boundary condition theta sigma prime. Okay, I just used the same decomposition here. I just applied to the partition function. So what happens here is that all these terms are positive. Okay, all these terms are positive. I mean, all these terms that I'm summing depending on theta, this depends on theta, they are all positive. So since they are all positive and I am summing over all of them, I can give a lower bound to this sum as being larger to this part of the sum calculated at some specific point, at some specific delta. So I will choose the delta, I will choose delta equals to sigma plus, right? So is the boundary is the condition that is that means that this is plus between lambda 2 and lambda 1. So all this sum will be larger than the sum of sigma prime inside the configuration space lambda 1 of the exponential of minus r lambda 2 lambda 1 beta t calculated at sigma plus times the exponential. Now, since theta will be sigma plus also between lambda 2 and lambda 1, this is just the plus boundary condition beta h plus sigma here. But now this term here doesn't depend on sigma prime, so I can factor this out from the sum. And then I finally get that the partition function in the larger box of h plus h prime is larger than the exponential of minus r lambda 2 lambda 1 beta t calculated at sigma plus times the sum. It will be the sum for every configuration of the Gibbs weight right here. So this is just, again, I recover the partition function, but now in a smaller system. Okay? So why this is important? Because since this is a lower bound, and now I am dividing by the partition function, this gives us, this implies that sigma a lambda 2 beta h plus h prime plus boundary condition will be less than the sum over all the configurations between lambda 2 and lambda 1 of what? Of the exponential of minus the difference, lambda 2, lambda 1, beta t eta, minus r lambda 2, lambda 1, beta t sigma plus, times what? Times the partition functions. So I will not write the indexes here, so I have space. I don't want to erase this part. So I have like this. So a ratio between two partition functions, okay? Times sigma a lambda 1 beta h with boundary condition eta. So now we have to distinguish two different cases. So the first one, what happens with what happens when eta is also sigma plus. So when eta is also sigma plus, then what is the red chalk? Do you see this color? Do you see this color? No? Yes? Do you see this color? Okay. So means that this part right here that I will call star. So when they are equal, then star is equal to 1. So suppose now that this is not equal to sigma plus, okay? So when I look to the reminder, okay, look to this expression right here, the reminder. Okay, thank you. Okay, thank you. So when I look to the reminder, okay, and I'm looking to this difference right here, the difference between eta lambda 2 lambda 1 beta t sigma plus. Remember, sigma plus is the configuration that's all plus. Then this will give me the sum of jxy 1 minus eta x eta y xy inside lambda 2 minus lambda 1. This corresponds to this term. Then there is plus the sum over x inside here, so lambda 2 minus lambda 1 y outside lambda 2 jxy. Then I have 1 minus eta x, and then I also have the term corresponding to the field h plus t 1 minus eta x. So notice that since we are in a ferromagnetic system, all these numbers are positive. So all the coupling constants are positive. So these are positive. These here are also positive. This is positive. This is positive, okay? And since eta x is not, since eta is not different, is different from sigma plus, then this implies that there exists an y here such that eta y equals -1. So for this y, this term here will give us 2. So these are all positive, okay? But in y, this will be larger than 2. So this term right here is larger than 2h plus t. So what this gives us is that this difference is lower bounded by 2 times h plus t. And since we have minus this difference, this gives us that sigma a lambda 2 beta h plus h prime, the plus boundary condition, will be less than now the sum over all the boundary conditions here of exponential, the boundary conditions that are different, okay, from sigma plus 2h plus t times sigma a and lambda 1 beta h eta, this term right here, plus what we want, lambda 1 beta h plus, okay? And by the inequality that I just raised, I know that this is larger than sigma a lambda 2 beta h plus. Okay? So taking the limit, t going to infinity, so I get the following. So this part goes to 0, okay? This part right here goes to 0, and I just get the remaining part. So I get the conclusion that I want. Sigma a 1 beta h plus. So again, since we defined the convergence of measures as being in the configuration space as being a configuration, as being as the convergence of all the means right here, of all the means of local functions, okay, of all the means of the local functions, and we show that all local functions are linear combinations of stuff like this. This theorem actually shows that the thermodynamic limit of the plus boundary condition measure is well defined, so it converges to some probability measure on the configuration space. So okay, so why this is important? We are heading towards the first, I guess actually the second big theorem on this course, that will be the uniqueness of the Gibbs measure, the absence of phase transition, and the uniqueness of the Gibbs measure, but we'll discuss this later. For the Ising model, when h is not 0. So remember the following. Going back to the pressure. So consider consider a sequence according to ZD and the Ising model with constant field, okay? Constant, actually translation invariant, okay? Translation invariant. In this case, translation invariant. Translation invariant. So, what can I say about this? So, about this, the sequence of local pressures with plus boundary conditions. So, if I consider H, okay, I can write the difference of the partition of the local pressures between beta H and beta 0 as being the integral 0 to 8 of the derivative with respect to H of this function. Beta H, okay, beta T, okay, and depending, now I'm integrating over T, so, okay, so, but we know exactly what this is. We know that this is the mean of the magnetization density, the mean, the expectation value of the magnetization density, beta T plus dt, where remember m lambda n was the sum, was 1 over lambda n, the sum of all the things inside the finite set lambda n, okay? So, what I just showed you, it will be an exercise now. So, notice that the field here is depending on t. So the integration over there is on t. So exercise, the first exercise of today will be show that for any t, okay, we have that the limit and go to infinity of this mean beta t in the plus boundary condition exists, okay? And now we can, since this is bounded, these are all bounded, you can use this to show that all of these functions will also be bounded, okay? They are bounded by 1, for instance. Oh, there is a hint. So use the previous theorem. Okay? This is the hint. Yeah, and what I want to use now is the dominated convergence theorem. So this is why I need this to be bounded, okay? So by the dominated convergent theorem, this implies that if I call this limit m lambda n lambda e plus as being mt, okay? These are measurable, bounded, and then I can use the dominated convergence theorem by the dominated convergence theorem. What this implies is that taking the limit both sides, here, taking the limit on triangle gives the following, gives that the difference between the pressure. Remember, all boundary conditions converge to the same value, and this is the pressure. So this will give us the following expression for the pressure. P beta 0 plus an integral 0 to 8 mt dt. So what would imply that this function is differentiable is the fundamental theorem of calculus. So if I can show that mt is actually continuous on 0 plus infinity, so this would imply that the pressure P beta h is differentiable on the same interval, okay? So this would solve the problem when h is positive. We will see next what we can do for the other case. So what is the strategy actually? So I know there is an exercise on the list. I don't know if you noticed, but on the first list, there is an exercise that shows that that asks you to show, right? To show that if you have a function on an interval, on an open interval, that is twice differentiable, then f is convex. Okay, f is convex if and only if the second derivative is the non-negative. Okay. So, and we also know that the limit of convex functions will be convex, and that convexity implies continuity. So, what we will do is try to look to the derivatives of this function, because this function with respect to the field is infinitely differentiable. You can differentiate it as much as you want. So then we get the following. First, look at the first derivative. Okay, so let's see how much time do I have. Okay, so yeah, I will do this. So lambda n beta t with the plus boundary condition. Remember this expression right here. So this is just, I just have to look what happens to the derivative with respect to one spin. Sigma x, the derivative with respect to the field in 1x plus lambda beta t. Okay. I already made this calculation with you Monday, I guess. So this is just sigma x, but now the field is constant, so I have this sigma y minus, this is plus lambda n beta t minus sigma x, the sum over y again, lambda n, sigma x plus lambda n beta t, sigma y plus lambda n beta t. Okay? And then I can rearrange this as being one, the mean here, between the sum overall. This means x and y, all the sides of the correlation between sigma x and sigma y. Sigma x and sigma y. Plus beta, I will not write the beta and t again. So this is the first derivative. And then, to use the exercise, we need actually to compute the second derivative. So I will let this also as an exercise to you. So another exercise. Another exercise here. So compute the second derivative. M lambda n plus lambda n beta n t. Okay? And show that actually the second derivative lambda n beta t, this can be written as the sum of x, y, and z inside lambda n of sigma x minus sigma x times sigma y minus sigma y, the mean. Not enough space. So you sum every triples here, then you get the sum of this product here. Sigma x, sigma y minus sigma y, sigma z minus sigma z, the mean. Where I'm writing this to denote the mean with respect to the local Gibbs measure with the plus boundary condition. Okay? So this is the second derivative. Okay? And there is also another correlation inequality that allows us to analyze this. Sadly, the usual GKS inequality is not enough to show what we want, something like this. So I will just state here without proof the GHS inequality. The GHS inequality says exactly that for any x, y, and z in lambda n, you have sigma y minus sigma y, sigma z minus sigma z, this expectation will be actually be less than 0. So this is actually negative, always negative. So this implies that although this doesn't show that the function that this function is convex, this means that if I multiply this by minus the minus sign, then this function will be convex. Each one of these functions is convex. When minus a function is convex, we call it a concave function. So this implies that the local magnetizations are concave functions. And then by similar arguments, just multiply by -1, the limit of concave functions will also be concave, and the concave function is always continuous. So this shows that the pressure given by this expression right here is differentiable every time you are in this interval. So what about the other interval, the other part of the real line? Ising spin systems, actually the kind that we study have a very special symmetry that many of you maybe already heard of, and it is the what we call the spin flip symmetry. But what is the spin flip symmetry? So spin flip symmetry. What is the spin flip symmetry? So we do the following. Define the map on the local configuration space. So you take an interaction and then you get an interaction that is given by the following. So S sigma x calculated at some point is just minus sigma x. So what you are doing is that since your system is just plus or minus 1 inside some finite set, what you are doing is that you are just flipping every side to the other direction. Okay? So what happens? Okay, so first notice that this spin flip symmetry, it has a nice property that when I apply it twice to a configuration, okay, then I just get the same thing. I just flip it twice. And also that it's actually a bijective map, okay, between the two configuration spaces. So let's see what happens when I apply the action of the spin flip to the Hamiltonian with a plus boundary condition. So what this means? So let me compose the Hamiltonian with a plus boundary condition with the spin flip. Okay? What this gives me? So remember the expression will be just jxy minus here the sum of the product of these two spins s sigma y minus the sum of x inside lambda and y outside jxy s sigma x times plus 1 minus the sum over all x inside lambda of h times s sigma x, the other way around. So remember, this is just minus sigma x, and this is minus sigma y. So this implies that the two-body interaction term of the Ising model is usually invariant by the spin flip symmetry. So if this Hamiltonian only had this part, the empty boundary condition part, so this means that we don't have anything of this, and this we don't have also anything like this, so just the empty boundary condition and the field equals to 0, then the spin flip would be a symmetry of the Hamiltonian. But since we have these terms right here, they don't allow the system to have this symmetry. So what happens is I have to write this Hamiltonian in terms of something that depends only on the configuration and don't have the spin flip anymore. Then I have to make some changes. For instance, on the boundary condition side, here I have minus x. But then I can take this minus x to this plus 1. So this will give me sigma x times minus 1. This plus 1 was, it is here because of the plus boundary condition. So if I get this to be minus 1, then now I'm changing the system to the minus boundary condition. And also, over here, similarly, since I have h times minus sigma x, I can write this as minus h times sigma x. So this implies that the spin flip action on the plus boundary condition Hamiltonian will give me the minus boundary condition Hamiltonian. The field will also be flipped. But this happens on the level of the Hamiltonian. So what would happen to the level of the measures, right? So remember, for any local function f, we wrote the mean of f lambda beta h plus as being what? As being the sum over all the configurations here of what? Of f sigma. And now I complete with the plus boundary condition. Okay. Notice I defined this only for the local configuration space, but you can define for anything. Okay. You can define for any configuration space, including the configuration space on the whole set. So this it's because when I rewrite the system, the measure, using this fact right here, okay, using this fact, this will be the sum over f applied s squared sigma plus lambda c, okay, times the same thing right here, plus beta h s squared sigma beta h. What this expression says to me is the following. We can write f s squared of sigma c plus. This can be written as f s applied to something that is inside here, lambda c, okay. And now what happens to this map? First, everything that is plus will become minus. So this will give me s applied to something, the minus boundary condition. The minus boundary condition outside. And then I call this flipped Hamiltonian part of the flipped configuration part as omega lambda. So I call the flipped part as omega lambda. This holds also for the Gibbs weight term. And since I wrote something like this, then the exponential of minus 8 plus lambda beta h as omega, okay? So this will be just minus h, the sum of lambda beta minus h minus the boundary condition calculated at omega. And since this is a bijection, summing over all the configurations is the same as summing over all the configurations omega. So this implies that f, the expectation value of x, beta h, plus this actually equals to f composed with x, the spin flip action, lambda n, beta minus h minus. Okay? This is the general expression. This is the general expressions of how the spin flip symmetry acts on this space. So I can use this to derive a similar result to what happens to the pressure for H negative. So consider H a positive number, and I can write the local pressure with the minus boundary condition between 0 and minus H as being the sum, as being the integral over 0 to minus H of the mean here, of lambda n minus beta minus H minus t, actually, dt. But then using this relation right here, okay, using the spin flip symmetry, this will actually be equals to the integral to 0 between 0 and H of m lambda plus the expectation value of the magnetization density with respect to now the plus boundary condition. And this we already discussed. This is continuous on the positive interval, so this means that this function right here, the pressure, if I take the limit, then the pressure on the other side will be differentiable. So okay, sorry. Yeah, you are doing something like this. You have the mean, okay? I'm writing just the brackets to mean the mean, okay? So this, sorry, you are asking about this, what this means? For instance, what this means? Yeah, x is a function, the function, like, okay. So this is abuse of notation, okay? Usually I write sigma x, but instead I should be writing sigma x. Remember, yeah, we have these functions right here for each subset of ZD, for each finite subset of ZD. Yeah. Omega x. So this should be written as like this, okay? Just abuse of notation. I'm just abusing the notation. Instead of writing x as a set, okay, I'm just writing it, just putting the x right here. And this usually denotes the function that, given the configuration, it will give me the value of the spin at omega x, okay? Okay. So this implies that the pressure is differentiable, okay? In all the region of the magnetic field for all beta, when H is not 0, okay? And remember, we showed that when the pressure is differentiable, the derivative, we show that the derivative of the pressure with respect to H would mean that the limit of all the magnetization densities, beta H, with respect to any boundary condition, would be equal to the derivative every time that the derivative exists. We showed this. So this, the fact that the pressure is differentiable outside every h that's not zero, so for h different than 0, this means that all these limits are the same, but we still don't know what this means to the Gibbs measures, because we have these limits existing only for a very special kind of observables, okay, of functions, of local functions, okay. This is not enough to see what happens to the measures, and to study what happens to the case of the measures. Then we will need another very important inequality that is called the FKG inequality, the FKG correlation inequality. So, but before going to the FKG, I want to say a few more words. First, this means this is a first consequence. Another consequence is that for the ferromagnetic spin systems, magnetic Ising with two body, okay, two body interaction. There can only be a phase transition when h equals to 0. This is, we will study the case h equals to 0 when we study, next week, when we will study something that is called the Pyros argument. And another interesting thing to notice is the following. I just showed you that the first derivative exists outside the region of h equals to 0. That doesn't mean to say that all the derivatives in the limit exist. Actually, this is a recent result, and if you want to check, the paper is this one, weak mixing. You want to check a proof of this fact, weak mixing, analyticity, of the pressure in the Ising model. By Sebastian Ott. This is a paper on the communications of mathematical physics in 2020. So a very recent one, very recent paper where they settled this question about the derivatives of the pressure. So, okay. The FKG inequality is another set of inequalities that can be applied to a very somewhat different class of functions that we already saw, and the functions were the occupation variables. So remember the occupation variables. for each A a finite subset of ZD, I have NA equals the product of X inside Y. This calculated at some configuration is 1 plus the configuration omega X divided by 2. Okay? And what special property this function have? Well, if I have, since the state space only have two values, okay, at each site I can give an order to it. So at each site I can give an order to the state space. And this order is just -1 is less than 1, okay? Less than 1. You only have two values, and I use this over here. So with this order at each site, I can give a partial order, into the configuration space. Actually, for any configuration space, they don't need to be local. And this partial order is given by the following. So if I take two configurations by the following. If I take two configurations, sigma, omega, inside here, then I will say that sigma is less than or equal to omega if and only if x is less than omega x or equal to for every x. For every x in lambda, okay? So, yeah. And now that I have a partial order, I can define what I mean by an increasing or non-decreasing function. So a function f is non-decreasing if every time I have two configurations here that such that they are comparable and one is less than the other, this will imply that f sigma is less than f omega. So non-decreasing. So for instance, show this is show that sigma x is non-decreasing. Sigma x is non-decreasing, and A is non-decreasing. Is non-decreasing for any A finite subset. So these are the occupation variables, and just 1 point. So this is just 1 point. And actually, this is a nice question. When sigma A is non-decreasing. And I mean for what a's we have. So this will show you the difference between the occupation variables and the spin variables. Okay. So the occupation variables, they are non-decreasing. They satisfy this property. We showed that they can also be used to write the local functions as a linear combination of them. So they also generate the continuous functions. Okay. So we can study, instead of studying the measures and taking limits and whatnot with respect to the spin variables, we can look what happens to the occupation variables. And then we can use the FKG, finally the FKG inequality. Inequality. So consider JXY positive, non-negative, okay, and HX a collection of real numbers, So this is the first difference. The FKG inequality holds for any field. This is the first difference from the Griffiths inequalities. The Griffiths inequalities, we had to ask every h to be positive. There can be no constant, but they need to be positive. And now they can be anything. But now we have a restriction in the system need also to be ferromagnetic, so the coupling constants also are non-negative, but they are only two-body now, only two-body. So then, for F, so you consider this for F and G non-decreasing. We have that F times G lambda n beta. I will write just H here, but I'm writing H to denote this family. H here. This will be larger than F lambda n beta H J lambda n beta H. And now the question, another difference between the Griffiths inequality and the FKG inequality is that the Griffiths, we showed it to the plus boundary condition, the empty boundary condition case. And the FKG inequality actually holds for any boundary condition. For any boundary condition. Okay. So what will I do now? So before we prove the FKG inequality, this is actually one of this inequality is very important. We use it everywhere. So before I give a proof of the FKG inequality, I want to go back to something that we did before, and to show a very important property that the local Gibbs measures satisfy before we prove this. So remember, at the beginning of the class, so we showed the following. That we could write the expectation value of sigma A lambda beta h with respect to the plus boundary condition. We wrote this as a sum 1 over the partition function of the sum over all the different configurations in a configuration space between two sets that are finite, okay, of the exponential of minus something, that was the error, the reminder, that depends only on the boundary condition, times the partition function, lambda prime, depending on eta, beta h, times this. Beta h, and now with respect to all boundary conditions. But what happens if we open all of this expression right here? So what happens is that we can use the decomposition of the Hamiltonian, okay, to recover the decomposition of the Hamiltonian with plus boundary condition, to recover that Hamiltonian again. So this R eta times the partition function lambda prime eta beta h is actually the sum over all the local configurations tau inside lambda prime of the exponential of minus h, the plus boundary condition Hamiltonian. Yeah, the plus boundary condition Hamiltonian in lambda, but calculated where? Calculated in tau omega prime eta lambda minus lambda prime. So plugging this again here and putting these two sums, this sum over here and this sum over here together, we get that the expectation value of lambda beta h plus will be actually equal to lambda beta h, the sum of all, let's say, omega here. So let me do this carefully because it may be confusing. So I will just put this over here, and then I get the sum over eta here, the sum over tau here. I have this the local Gibbs weight calculated with the plus boundary conditions calculated at eta at tau lambda prime eta lambda minus lambda prime times this lambda 1 beta lambda beta h lambda prime, right? Here I have lambda prime eta. Okay, now I will combine these two sums again. So I will sum over all the configurations inside lambda. And notice that when I rename these variables as omega, so this boundary condition will also change to omega. You can also check that these functions doesn't depend on the spins inside lambda prime. So this will be the sum over all the configurations here. Now a at omega lambda prime beta h times the exponential lambda beta h omega. So again, I wrote using the previous calculations. I had a very important relation between what happens to the expectation of some of this function in a box to the expectation of what happens inside the box, but in a smaller box with respect to all boundary conditions. Yeah, exactly. What we did is inside here, but you can actually show that something similar would be true if I didn't have this. The problem is that if I don't have this, then I would have to carry something that is fixed outside here, so a product of something that is outside. Okay, so then this is just the mean, the mean with respect to the plus boundary condition of this function right here, the function that associates of this function. Where this is the function, where this is the function lambda beta h is the function that associates to each omega, associates the mean like this. So it's not so hard to see. Actually, with a little bit of care, you can show that a similar relation holds when a is not here, is not inside here. It can only be inside lambda. And you can also show that this equation actually holds for any any local function instead of sigma a, it will hold for any local function. And some of you may already have recognized this. This relation that the local Gibbs measures have are called the DLR equations. These are the DLR equations. So, yeah. Yeah, it's a consistent condition. And more than that, it's not only a consistent condition. In more general contexts, the DLR equations says that you know what are the conditional expectations of your measure, and the conditional expectations are given also by local Gibbs measure. Okay. So, okay, I will stop here. Next class I will prove tomorrow. Tomorrow is Thursday. I will prove FKG, the consequences, and also I will show how to use the DLR equations in nice way.